Mechanical sealing. Mechanical seal failure. All mechanical seals will eventually wear out, but some of these seals will last years, while others will fail prematurely. What causes or factors are involved in determining the eventual life of a seal? What are some of the root causes of mechanical seal failure? This instructional segment discusses some of the most common reasons for seal failure. Misinstallation of mechanical seals. Seal faces opening during operation. Improper seal selection. Poor design. And inadequate environmental controls will be presented. Misinstalling mechanical seals will lead to seal failure. One of the most common mistakes made during installation is setting the seal at the incorrect installation dimension. Common causes of this are not tightening up the pump well enough when marking the shaft initially, reading the installation print incorrectly, using the wrong print, or making measurements incorrectly. Many times during seal installation, the stationary and rotary seal faces, and even the secondary seals, such as O-rings, become damaged by handling if proper precautions are not taken. For a seal to work reliably, the seal faces must stay in contact at all times. A common cause of seal failure is that the seal faces open during operation. Seal faces can open for a variety of reasons, but most of them are equipment related. When the seal faces open, particles will penetrate between the lapped faces. When the faces close, the solids may prevent the faces from completely closing, or the particles may embed into the soft seal face. A deep wear track found in the harder seal face caused by the soft face is evidence of this phenomena. Seal face opening can be caused by radial and unbalanced forces acting on the impeller. These forces can cause shaft deflection and vibration. Pump cavitation and poor coupling alignment also have detrimental effects on mechanical seals. A very common cause for seal face opening is stuffing box misalignment. That is, the stuffing box face is not perpendicular to the center line of the shaft. Let's take a close look at why this lack of squareness will open seal faces and eventually cause seal failure. Let's begin by looking at a simplified cross-section of a standard back pull-out pump. In this example, the face of the stuffing box is not at 90 degrees to the axis of the shaft. The broken line represents perfect alignment between the stuffing box and the shaft. The solid line indicates misalignment. When a standard rotary type mechanical seal is installed in this pump, the spring-loaded rotary element will force itself square to the stationary to form an effective seal. The rotary is designed to operate parallel to the shaft, but because of misalignment, this is not possible. This simplified working model has the degree of misalignment exaggerated to demonstrate the negative effects more clearly. The springs near the bottom of the model are more compressed than those at the top. The rotary element has cocked itself at an angle in order to stay square against the stationary. As the shaft begins turning, the rotary has remained cocked on an angle. The springs are compressing as they approach the bottom of our screen, extending as they reach the top, keeping the seal faces mated. To accomplish this task, the springs must fight continually against the tendency of the spinning rotary to try to straighten itself out. Because the rotary is a spinning mass traveling at a high rate of speed, it begins to act like a gyroscope. And whether it is a child's toy or part of a space-age navigational system, a gyroscope does not like to be pushed off its original axis. Acting like a gyroscope, the rotary is desperately trying to run parallel to the axis of the shaft. It is pushing with tremendous force on this part of the stationary. Only spring compression and fluid pressure are keeping the faces mated at this point. The rotary is actually trying to pull away. The major problem created in working against this powerful force is seal failure, caused by the seal faces opening and letting solids penetrate between them. To prevent seal faces from opening, it is imperative that seal designs maintain face flatness over a wide range of temperatures and pressures. In recent years, finite element analysis has given seal designers insight into the response of seal face flatness to changing pressures and temperatures. Maintaining face flatness in a mechanical seal is one of the keys to longer seal life. Improper seal selection can lead to seal failure. The chemical resistance of all the wetted seal components must be looked at. The three general areas of material selection are the metal components, the secondary seals, and the primary seal faces. The metal components such as the sleeve, holder, gland, and springs must be investigated for the proper corrosion resistance. This is especially critical with thin metal parts, such as metal bellows and springs. The secondary seals of the mechanical seal must also perform well in the product. Will the elastomer perform well in the pumped product at all its temperatures? Elastomers subject to too high a temperature will compression set or harden, leading to seal failure. Chemical attack can cause an incorrectly selected elastomer to become sticky or swollen and lose its physical properties. Another critical area of material selection is the seal face materials. Are the materials acceptable in the concentrations and temperatures of product that they seal? For instance, carbon may be attacked by strong oxidizing chemicals such as nitric and sulfuric acids at certain concentrations and temperatures. Make sure the face materials are constructed of pure, unfilled materials. Otherwise, binders and fillers can be attacked as well. Seal design must be considered. Poor seal design can lead to early failures. The correct seal design must be chosen for the application. Design areas such as balance versus unbalance and fretting versus non-fretting must be considered. Does the seal have the necessary anti-clogging features? Is it relatively easy to install all the parts properly? These considerations must be answered to select the right seal for the application. Environmental controls create a proper environment for mechanical sealing reliability. Lose the environmental control and reliability is lost, usually with imminent failure. Loss of environmental controls can happen for a variety of reasons, such as loss of source pressure or simply a valve being closed. Pumping systems are frequently characterized as static systems, but tank levels are changing, causing system curves to change. Valves modulate flow rates by increasing friction. This also changes pump requirements. These changing systems cause pressure changes inside the stuffing box. Environmental controls must be adequate at all operating points to work reliably. Inadequate environmental control is a very common cause of seal failure. Some of the root causes of mechanical seal failure are misinstallation, seal faces opening, material selection, poor design, and inadequate environmental controls. Each one of these will eventually determine the life of your mechanical seal. To ensure maximum reliability, each of these factors must be addressed.